In the first part of general physics, there's a lot of considerations for gravity. And rightfully so. Gravity is one of four fundamental forces of nature. You can essentially take all of the physical universe and boil it down to four fundamental forces. Gravity is absolutely one of them. And in the second part of general physics, we get to another one of the four fundamental forces of nature, which is the electromagnetic force. And so most stories of the electromagnetic force begin with a charge. And when a charge has the presence of another charge, there is a Coulomb force that both charges exert on each other. And so while we're dealing with charges now, the structure of the Coulomb force is actually very similar to what you were doing with gravity, where with gravity you knew that if you had two objects and those objects had masses, that the gravitational force between those masses was proportional to the multiplication of their masses, and it was inversely proportional to the square of the distance between those masses. So as the masses got closer and closer, the gravitational force grew exponentially. And so similarly with the Coulomb force, if you had two charges, it turns out the Coulomb force is also going to be proportional to the multiplication of the charges. And it's also inversely proportional to the square of the distance between the charges. So as two charges get closer and closer together, their Coulomb force is going to exponentially increase. Now, that being said, there's two important differences. The first difference is that gravity is only an attractive force. When you have two masses, the gravitational force on each of those masses is attractive. Mass 1 is attracted towards mass 2 is attracted towards mass 1. Now, if you have two charges, Q1 and Q2, the Coulomb force can be either attractive or repulsive. It depends on the sign of the charges. So for instance, if Q1 was a positive charge and Q2 was a positive charge, then they would both have the same sign. And it turns out when they both have the same sign, that means that the Coulomb force is going to be repulsive. So if Q1 was positive and Q2 was positive, then the two charges would repel each other. Now, if Q1 was negative and Q2 is negative, while they have negative signs now, both signs are the same, negative. And so two like charges repel, and so if Q1's negative and Q2's negative, they're still going to repel each other. But if Q1 was positive and say Q2 is negative, now they have opposite charges. It turns out opposites attract when it comes to charges. And so it would be an attractive Coulomb force. Or if Q1 was negative and Q2 was positive, again, now you have opposite signs, and so those would be attractive forces. So you have to take note of the sign as to whether it's an attractive or repulsive force, whereas with gravity, it's always an attractive force. Now, it turns out that the Coulomb force is inversely proportional to the square of the distance. So again, as the charges get closer and closer, whether it's attractive or repulsive, that force is going to exponentially increase. Here's the other big difference between gravity and the Coulomb force. Now remember, again, gravity is only a one-way attractive force, whereas the Coulomb force can go both ways. It can be attractive or repulsive based on whether the charges have the same or different signs. But here's the other thing. The constant that is multiplied when you calculate the gravitational force versus the constant that is multiplied when you calculate the Coulomb force, they are drastically different. The gravitational constant is of order of magnitude of 10 to the minus 11. And in contrast, the Coulomb's constant, that's the constant that you multiply by the multiplication of charges and divided by the square of the distance between them, that is of order of magnitude of 10 to the 9. So if you were to take a ratio of the constant you multiply the Coulomb force by versus the constant that you multiply the gravitational force by, it would be 10 to the 9 divided by 10 to the minus 11, which is of order of magnitude of 10 to the 20. So to put it in perspective, like 10 to the 9 is a billion. So 10 to the 20 would be 100 billion billion. In other words, the Coulomb constant is 100 billion billion times stronger than the gravitational constant, which is to say that the Coulomb force is way, way, way stronger than the gravitational force. One more thing I want to leave you with here with respect to the Coulomb force is a transition to the notion of a field. You're going to encounter the idea of electric fields and magnetic fields in this course. And so let's start with the electric field. Electric field is very related to the idea of Coulomb force. Essentially, if you have one charge, you can draw a field around that charge where you can think of that field as a potential Coulomb force in the weighting, where if you brought a second charge in and you placed it at some point in that field, then the Coulomb force experience would simply be the charge that you brought into the situation multiplied by the electric field that was there by the presence of the first charge. Because remember, you have a Coulomb force between two charges. So if you have just one charge, you could draw this map of what hypothetically, if you brought a second charge in, what the Coulomb force would be when you bring that second charge in. And that hypothetical map is the electric field that surrounds the first charge. So think of the electric field as the force per charge. If you look at the units of the electric field, it's going to be newtons per coulomb, i.e. force per charge, such that if there's a single charge and it has a field that surrounds it, if you take a second charge and you place it somewhere in that field, you simply multiply the second charge by the electric field value, and voila, you have the Coulomb force between those two charges. So when you have a single charge, the electric field that you draw around that charge is simply this hypothetical map of if you brought in a second charge at a certain distance away, i.e. in a certain location in that field, if you were to take the charge number 2 that you just brought in and multiply it by the electric field due to the first charge, then you would have the Coulomb force between both of those charges. So just a quick summary. The Coulomb force involves two charges. It involves a distance between the charges, and it actually has a very similar structure to the gravitational force. You multiply by the values of the charges just like you multiplied by the values of the masses. And it turns out that both the gravitational force and the Coulomb force are inversely proportional to the square of the distance between either the charges or the masses. But the big difference is that the multiplying constant for gravity, which is of order of magnitude of 10 to the minus 11, versus the multiplying constant for the Coulomb force, sometimes called the Coulomb's constant. So the gravitational constant often is a capital G, and the Coulomb's constant is often a lowercase k. The Coulomb's constant is on an order of magnitude of 10 to the 9. And so the ratio of the Coulomb's constant to the gravitational constant, 10 to the 9 divided by 10 to the minus 11, is of order 10 to the 20, which is 100 billion times. Coulomb forces are 100 billion times stronger than gravitational forces. And also, Coulomb forces can either be attractive or repulsive, whereas gravitational forces are only attractive.